Our second example is with a function g of x called x cubed minus 3x. And that is another polynomial. And again, just to get a sense of the function first, I've graphed it here. And I can see that it's got a relative max and a relative min. And it does change from concave down to concave up. I'm going to guess that happens at the origin, but we'll see. So again, what is my goal? I am trying to find the locations of the maxes and mins and inflection points on this function. So I start by taking the first derivative, g prime, and setting it to 0. And I get two solutions, x equal -1 and +1. And then what I'm doing next, instead of the table like I used with function f previously, I'm just picking these test x values. These are the x values, and comparing the y value, the sign of the y value. So I set up a number line. On the number line goes the roots, x equal -1 and x equal +1 of g prime. So I'm putting the roots of the derivative, critical numbers, on a number line. Then I'm using a test point, x equal -1.5, something to the left of -1. And I check the sign, SIGN, of g prime, and I see that it's positive because I got a positive 3.75. Then I pick an x value between -1 and 1, and I picked 0. And I ask for g prime of 0 so I can see the sign of g prime, and I got a -3, so g prime is negative for x's between -1 and 1. And then I picked an x value to the right of 1, and I picked 1.5. Again, any value to the right of 1 will do. You could have picked 2, you could have picked 10. I picked 1.5, and I evaluate g prime, not g, but g prime, because I want to know the sign of g prime. And my output was 3.75, which means g prime is positive. So what I know now about g is that it's increasing until x equal -1, and then it decreases until x equal 1, and then it increases after x equal 1. So that tells me I have a relative or local max at x equal -1 and a relative or local min at x equal +1. And I've plotted here again g prime just to make sure that you're remembering what we did from chapter 2. So where I can see the roots on g prime at 1 and -1, and then remembering where g prime is positive, f is increasing. Where g prime is negative, f is decreasing. Where f prime is positive, f is increasing. So you can relate those to the graph of f above. And then I want to find possible, here I use, so this is again the first derivative test. Stop! No. Stop. I was using the first derivative test. Sorry about that little interruption. Now here I'm actually using the second derivative test. I'm finding I found g prime of -1 is 0, and now I look at what is the sign of g double prime at that spot, and it's -6, so the sign is negative. That means g has a relative max at x equal -1. And then I had found up above that g prime of +1 is 0, so using the second derivative test to find maxes and mins, I check the sign, SIGN, of g double prime at 1, and I see that the value I get is positive 6. So g double prime of 1 is positive. So those two things together tell me that g has a relative minimum at x equal 1. Okay, so this is the second derivative test. And you really don't need both. I'm just demonstrating for you. You could do either or. When you're finding maxes and mins, you could use a first derivative test, or you can use a second derivative test. I'm just demonstrating both so you can see how they both work. Okay, and then I found g double prime, or I asked Mathematica to find it. It's a nice line equation, 6x. And I set that equal to 0, and I got x equals 0. Okay, and then I checked the sign, SIGN, of g double prime on either side of that. So I create a number line, and I put the root of g double prime on my number line. So I set g double prime equal to 0, and my solution was x equals 0, and that x equals 0 is what's on this number line. And then I pick a point to the left of 0. I picked -1, and I check the sign of g double prime. I evaluate g double prime at -1, and I get a -6. So that negative sign tells me g double prime is negative to the left of x equals 0. Then I pick an x value bigger than 0, and I picked x equal 1. And I plug that value into g double prime to find the sign, and that is a positive. So that tells me that g is concave down to the left of x equals 0 and concave up to the right of x equals 0. So g has a point of inflection at x equals 0. And again, not a bad idea to plot the second derivative just to confirm everything. So there's that one root there, and to the left of the y-axis, g double prime is negative, and to the right, g double prime is positive. That tells me about the concavity of g. All right, so g is concave down to the left of the y-axis, and g is concave up to the right of the y-axis. You could also note on the first derivative graph here, but again, I don't want to make it too crowded, you could split this first derivative graph along the vertical axis there, and to the left of the vertical axis, f prime is decreasing, which means f is concave down. To the right of the vertical axis, f prime, the graph I'm looking at, is increasing, which tells me that f is concave up there. So again, it all matches, and it's good for you to check and make sure that everything matches up.